Hello everyone. In this video, I am going to discuss with you the Norton's theorem. Just like Thevenin's theorem, Norton's theorem is a method used to simplify complex linear circuits. Given this circuit, we have 15 volts as our voltage source, a 3 ohm resistor, a 4 ampere current source, a 3 ohm resistor, and a 6 ohm resistor connected in parallel. We now have our Norton equivalent circuit, which have a Norton equivalent current, a Norton equivalent resistance, and a load resistance across A and B. Step 1. For solving the Norton equivalent circuit, we must find its Norton equivalent resistance. And in finding the Norton equivalent resistance, we must remove our load. Our voltage source is assumed to be shorted, and our current source is assumed to be open. And that leaves us a circuit with 3 ohm resistor in series with another 3 ohm resistor that is in parallel with our 6 ohm resistor. So let us now solve for our Rn. We have 3 ohm plus another 3 ohm. That leaves us 6 ohms. 6 ohms is in parallel with another 6 ohms. That is 6 ohms over 6 plus 6 equals 12 ohms. And that leaves us 3 ohms. So we now have our Norton equivalent resistance, which is equal to 3 ohms. The next step is finding the Norton current. Our load resistance is assumed to be shorted, and our Norton equivalent current is assumed to be the short circuit current in this. So the first step in solving for our Norton equivalent current is to find the voltage on this node. And by using nodal analysis, let us solve for the voltage within this node. That is 15 volts minus voltage on the node. Let us assume that is V sub 1 over the 3 ohm resistor plus the 4 ampere current equals that voltage on that node V sub 1 minus 0 volts over 3 ohms. Let us multiply the whole equation by 3, and that leaves us 15 minus V sub 1 plus 12 and equals to V sub 1. Solving the V sub 1 using algebra, that leaves us 13.5 volts. So we now have our Norton equivalent resistance and our voltage on this node. So in solving for the Norton equivalent current, let us use simple Ohm's law. That is, current I sub n equals the voltage on this node V1 over the Norton equivalent resistance. That is equals to 13.5 volts over 3 ohms. And that is equals to 4.5 amperes. And now we already found our two parameters for solving the Norton equivalent current, or rather circuit. And that is our Norton equivalent resistance and our Norton equivalent current. So for solving the current on the load, the formula can be used. R sub n over R sub n plus the load resistance R sub L times the Norton equivalent current. And that is equals to the current on the load. Thank you everyone. Please don't forget to like and subscribe to our channel. Thank you. Hello everyone. In this video, I am going to discuss with you Thevenin's theorem. Thevenin's theorem is an analytical method used to change a complex circuit into a much simpler circuit with a voltage source, or our Thevenin equivalent voltage, a resistor in series, or we can call it our Thevenin equivalent resistance, and our load resistance. So given this sample circuit, we must find its Thevenin equivalent circuit. So here it is. Solving for the Thevenin equivalent circuit can just be summarized in a few steps. So step 1, we must remove the load resistance of the circuit, which is this 40 ohm resistor. And then we must find the Thevenin equivalent resistance. And in order to do so, we must treat all voltage sources, this 10 volts and this 20 volts, as shorted, and our current sources, which we don't have in the circuit, as open. So assuming this is shorted, we now have a straight line, and this load resistance removed, we can solve for the Thevenin equivalent resistance, which is 10 ohm in parallel with our 20 ohm resistors, and that is equal to 20 times 10 over 20 plus 10, and that will give us our Thevenin equivalent resistance, which is 6.67 ohms. So the next step in finding our Thevenin equivalent circuit is to find for the Thevenin equivalent voltage, or our VTH. So first, we must find the current flowing around the loop, and that is equals to 20 volts minus the 10 volts all over 20 ohms plus 10 ohms, and that will give us our 0.33 amperes, or equals to 330 milliamps. This current of 0.33 amperes is common to both resistors, so the voltage drop across 20 ohm and 10 ohm can be calculated as 20 volts minus the 20 ohm times 0.33, and that will give us 13.33 volts across A and B. Same with 10 volts plus 10 ohm times 0.33, and that will also yield us 13.33 volts, and that is common on both resistors. So the required parameters of our Thevenin equivalent circuit are now met, with our Thevenin equivalent voltage, or our VTH, to be 13.33 volts, and our Thevenin equivalent resistance, which is 6.67 ohms. So the last step is to find the current flowing around the whole circuit, and that can be calculated as 13.33 volts over our Thevenin equivalent resistance, which is 6.67, plus the load resistance, which is 40 ohms, and that will give us our current, which is equals to 0.286 amperes, or 286 milliamps. And that's how we solve our Thevenin equivalent circuit. Thank you.